Aloha. In this video, we're going to do the binary search tree iterator assignment. And if you look at my screen here, it's our assignment 10, and it's out of chapter 19. So the book, it's the same as project 4 in the book. They give you most of the code. Well, they give you all the code for the class, for the BST class, which is in the book, and then also I've added the start of the my BST class, which is what you're extending, or you're extending the BST class with this my BST, and it's this BSTIterator is something you're adding to that. This part is available in the previous two assignments, so I just added it in there. This assignment is for us to complete this BSTIterator class. And to review what an iterator is, let's go back to chapter 18 when we were introduced to linked lists. And this section 18.2.2 describes implementing a linked list, and it describes all of the methods and shows some nice pictures here, how you'd add a node to a linked list, how you implement adding a node at the end of the list, inserting in the middle, and so on. And then down at the bottom, it gives you the code for a linked list class. And in here, you see that there's a bunch of methods that are described above. And down here, we have this iterator. Now, what's an iterator? Well, an iterator is like a loop index. Like if you had a loop to traverse through each node of the linked list, that's kind of what an iterator is. So if we go 2 sections further to this to section 18.3, we talk about iterators. And an iterator is an object that provides a uniform way of traversing the elements in a container object. So in this case, chapter 18, we're talking about traversing a linked list. And in our assignment, we're talking about, in this assignment, in assignment 10 here, the BSTIterator, we're talking about traversing a binary search tree. So instead of a linked list, it's a binary search tree. But so we can understand how the concept of an iterator here, down here describes some code that is used to test the iterator, basically used to test this iterator in this code. So this code here imports this code, and then it creates a new instance of a linked list called LST. It adds 1, 2, 3, and -4, in this case -4, to the list, and then it displays it out. Okay, and then what it does is it creates an iterator, and this is from this iterator class, from this thing down here, linked list iterator. And then it traverses through using the iterator as the index. And so when we actually run this code, we can change this to -2, 5, 4, just to show you that it's different. And when we run it, we see that it this right here is this here, and then these 5 statements here are 1, 2, 3, 4, and then the 5th one causes an error, and so we see this traceback here, and it's this stop iteration exception was raised on line 197, which we see is here, this thing. So anyway, that's how an iterator works. So in a binary search tree, with the binary search tree, the definition of a binary search tree is that all the nodes on the left of the root are less than the root, and all the nodes on the right of the root are greater in value than the root. And each subtree is also a binary search tree. Here, this is an example of a binary search tree. We have 50, and then all the nodes on the left are less than 50, and all the nodes on the right are greater than 50. And this also is a binary search tree because all the nodes on the left are smaller and all the nodes on the right are bigger. And so if we were to add like 85, that would go here. So 85, enter, and see it goes here. If I were to add 60, well, that would have to go off the 80, and that had to go over here. So I go 60. See, so that goes over here. If I do so if I do 55, it goes off of here. If I do 52, it goes off of the 35. So if I go 52, it goes off. Oh no, 52 is greater. I'm sorry, 52 is greater than 50, so that goes on this side. It's less than 60. If I do 48, that would go like over here because it's greater than 35 but less than 50. Anyway, so that's a binary search tree. Now, traversing through a binary search tree would probably mean starting from the smallest one, and each time you hit this iterator thing in the actual problem in our assignment, it's first we load up the binary. First we load up the binary search tree, and then we traverse it. We create an instance of an iterator, and then we traverse it with this while loop. We keep on looping while we keep on looping until we hit this exception, and the exception will display out this message, all is traversed. So that's this here. So if we were to actually enter, well, we could enter this tree, this, into here to see what it looked like, but I don't think we're gonna have to do that. Okay, so so this here is the binary search tree starting code, which is this code up here, from here up. And then you are to create my BST, which extends BST, this class up above, and we're going to add this iterator definition here, which is this ITER, which is what we talk about when we create here ITER, for example. So that just returns a BST iterator. And what's a BST iterator? It's one of these things. It's one of these objects. And it's an instance of this object. Now, how does this object work? Well, first of all, when you initialize it, meaning like when you do when you initialize it, anyway, the initialization of it, you execute this getList method, which is what you actually have to write, And all that is it, gets a new list. It's going to keep track of its own list. It's going to keep track of the list as you iterate through. And so that's going to be contained in this object. And then each time you hit next, which is like this, each time you hit next, it is going to it's going to go to the next one. First, it increments this current property of the list, and then it's going to set the one at just the one right behind it. We've incremented to the next one, and then we return the list from the previous one. Okay, so we return this node. Okay, and so when we come in here again, if this current if the self value is over the edge, in other words, if we're done, if current is greater than the length of the list, then we raise this this exception. So anyway, so our job is to write just this code. It's to write this getList, and we're going to write it. So we're going to create the list so it's in order. So so when we traverse it, one element at a time, it's going to produce an output that is in order. That is, like for this one, it would traverse this way, where first it's 20, 25, 35, 48, 50, 52, and so on, 60, 80, and 85. That's that's an in-order traversal. It goes down and does this one, then nothing here, then this one, 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 nothing here, this one, then this one. And that's the in-order traversal. So let's open up let's create a new folder called BSTIterator. Let's see, new folder BSTIterator. Okay, and then let's go inside. And let's open up a CMD. And let's CD to here, click Control C, CD paste. Oops. And let's do a code period. And we open up Visual Studio Code. And let's create a new file. Click. And let's paste in this code. Shift click copy, paste. All right. Let's save as main.py. Okay, here we go. Here it is. And all we got to do is write this code. So, all right, so let's let me pull up my notes here. All right, a depth, I mean, an in-order search, an in-order traversal is going to be first you traverse the left tree. So let's start out here. We're going to return. First, we're going to return the left tree. So self.getList. This is going to be a recursive method. The root that's me. That's where I am. Left. So this is the left tree, the left child, the tree off to my left as my left child. And so you're going to return that. And then after that, it's going to be the root element. And then after that, it's going to be the right list. Okay, so basically what this is we are, when we have to return the list, this is the list that we're going to use when we traverse, when we initialize this iterator, and then we traverse through the iterator, okay? One node at a time. But before we do that, we have to generate the list. We have to generate the path, and that's what this is. And it's a recursive definition where the list of the root is going to be whatever the list of its left child is, and then itself, and then whatever the list of the right child is. Okay, so how does this end, or how does it terminate, or it's keeps on calling itself? How does it know when to return? Well, it knows when to return when you ask it to get the list of a non-existent node. So when the left child of the root is nothing, in other words, it's not there, then this is going to be nothing. And when the right one is nothing, then this is going to be nothing. So the termination condition looks something like, if the root is none, in other words, if it's null, then we want to return nothing. Okay. Otherwise, elif the root of the left is nothing. I need to make this a double equal. If that's the case, then we return the there is nothing on the left, so we end up returning the root element. That's me, concatenated with, followed by the get list of the right of my right child. Okay, that's if my left child doesn't exist. If my right child doesn't exist, then I guess it's something like this. Right. It's going to be left. Otherwise, it's going to be this. So if it has a left child and it has a right child, then it's going to execute this. And what this is first go find the list, a list representing my left, the tree off to my left, and then I'll stick myself in there, and then go off and return to me a list which represents the tree that's off to my right. And then if either the left or the right doesn't exist, but the other one does, then it executes, whichever one is appropriate. And if it actually hits nothing, in other words, if you're asked to return, in other words, if this is executing and you don't really have a left node, a left child, then when this thing comes in, this line is going to be true, and then so it's going to return nothing. All right, so I think that might do it. So what happens when we execute this? Let's see, how about if I try executing it this way? Run. No. How about this one? Run. Oh, run. What happens? Oh, debug configuration. Oh, this one. And so this is what happens. Okay. Ooh. Oh, enter integers in one line for tree separated by space. All right, what would that be? Let's see, it's be this here. Copy. And I can go paste, enter. All right. That looks right. 1, 2, and that is a result of this. I gotta save this. So that's quickly goes away. All right. Oh, this should not be there. We go. Gee, that's amazing. That's just a warning, probably. Anyway, so it's executing these here. This for each one of these that is printed out right here, that executes. If I were to actually change this and get rid of this, get rid of this, then it would print one line at a time. So let's do that. I'm going to save this. And let's run this again. Run this one. And let me paste this in again. Yep, 2, 3, 5, 8, 9, 12, all traversed. All right, so I hope that helps. Thanks for watching.